Okay, so we're going to start section 14.1. I'm going to try and get the chat visible and also my participant window. The hand raising thing works sort of okay. It's not great because I don't see all of your names at once, but I will be looking periodically to see if a hand is raised and also if someone's typed a question. You know, again, it won't happen spontaneously, but I will be looking through this as we go. But any of you that do have microphones, in every case, you may unmute yourself at any time and interrupt me. So don't be shy about that at all. Okay, I see no questions, so let's go ahead and begin. So 14.1 is on functions of several variables. We're done with chapter 13, which was all about space curves and velocity. You know, we talked about curvature and we talked about velocity and acceleration. And we had derivatives that were functions of a single variable, because the space curve, being one-dimensional, is describable through one parameter, which was time in that case. When we do functions of several variables, we tend to set time aside, even though it doesn't have to be set aside. Time can be a variable, but right now we tend to kind of freeze time for these just because when you talk about position and time, that's almost like space-time. And that's more of a relativity in physics topic where you will see functions of 4 variables which are space and time. We'll leave that to physics. Okay, so let's go ahead and get started. But these are scalar values, so they have a position input, usually a position vector. Could be 2 or 3 dimensional. And a scalar output. So this is not vector valued. And so there will just be fewer vectors here. There's still vectors, right, with the position vector input. But we won't see a lot of vectors until we get into directional derivatives, I think. So that'll take a little while. Okay, so let's go ahead and just do a quick example. Let's say f of x, y, so that's one of 2 variables, is 9 minus x squared minus y squared, like that. So to graph, let z be f of xy. So that means it's z equals 9 minus x squared minus y squared. Okay. Obviously, this is a surface. And it turns out it's an inverted paraboloid. Okay. Sometimes we'll do level curves, which are essentially traces where z is set to a constant. And we defined a trace back in chapter 12, where you set a variable to a constant. So level curves are traces. And a trace is something, again, we covered back in chapter 12. Traces, those are plane curves where z is equal to a constant. So if we do the level curve z equals 0, then we're saying 0 is 9 minus x squared minus y squared. So that's just x squared plus y squared equals 9. And that's a circle of radius 3. Okay, that's when z is 0. Okay, any questions? Okay, and then if we set z equal to 5, and you can see I'll be picking very carefully for my z heights so that I end up with a nice radii on my circles. Okay, so with z equal to 5, I have 5 equals 9 minus x squared minus y squared. So I think that's x squared plus y squared equals 4, right? So that's a circle of radius 2. Okay. And then we'll do z equals, okay, how could I get a 1 out of that? So if I did z equals 8, so we would have 8 equals 9 minus x squared minus y squared. So of course that's a circle of radius 1. Okay, and then let's do z equals 9, and that'll kind of be all we have. So z equals 9 will give 9 equals 9 minus x squared minus y squared. And of course, that's x squared plus y squared equals 0. And you can call that a circle of radius 0, but I would rather call this the point 0, 0. And I'll go ahead and say 9 because the z coordinate is 9. Actually, I think I'll leave it out because that's not part of the two-dimensional curve. This is a curve that's just a point. Okay. And so now, easy enough. Here's the point. And I'm just going to draw, that doesn't look like a circle. I hope it comes out right. There we go. And then another circle. I'm just drawing sort of concentric circles who have the same center. Not well, but there they are. Okay, so, and then it's nice, this is basically a topo map. And on a good topo map, these are called level curves. Because everywhere you go on the curve, you get the same height. And if you walk on the curve, if it was like a trail that you were following, it would be perfectly level. So on the furthest out one, that's where z was 0. So I may even put these elevations on here. I'm going to zoom in. So the first one, z is 0. Then the next one, z, I think was 5. Then z was 8. And finally, z equals 9 in the origin there. Like that. Okay, any questions? And maybe, let me just grab a topo map. Let's see if we can find a topo map to paste into this. See if we can find a good one here. That's not what I want. There's a good one there. I think I might be sorry. Yeah, that's great, actually. So these are level curves on the topo map. And if you kind of zoom in, you can see that on these level curves that elevations are drawn. And as long as you move anywhere along one of these level curves, you're not going up or down, you're not rising or falling. And I didn't mean to get that. And I'm gonna do a real quick little screen capture here. I hope that worked. If it doesn't, then I'm just gonna ignore it. There it is. Okay, and on a topo map, I'm not sure what they call these level curves, but if somebody asked me what those lines were, I'd say they're level curves, and you can see the elevations anywhere, and you get a sense for sort of the geography. Maybe it's a little harder to see here, but if I was to graph this thing, you know, the inverted paraboloid sort of, this helps me see what the paraboloid looks like. So I've got these level curves that we've sort of been drawing. Okay, and then let me go ahead and I'll do some dotted lines here. You see the back side of the level curves. And maybe I'll add some radii to these. So here, I think my radius, was that a radius of 2 right there? And then maybe down here, that was a radius of 3, and so on. Okay. Of course, we could give z-coordinates here. So the z-coordinates at first are 5, and then way up here we have an 8, and the very top is where z is 9, as we know. Okay. So those are level curves. When we draw the level curves on a surface, they're called contours. So this is also called a contour map over here. Okay, so I'll just go ahead and say, I'm not going to write all this out, but just to say that the level curves are called contours. So sometimes, again, they'll call it a contour map. Okay, Now I'm looking to see if you guys have any hands up. I see multivariable functions has a hand up. So basically this is a top-down view. If you set your function equal to z, and a side view, if you set the function equal to y or x. Yeah, I just think what you're doing is when you look at the level curves, I think of this as just making the z coordinate 0. So when you look at this topo map here, sorry, the map of level curves, you're just looking down on it as in the same way that you look down on a topo map, where the level curves, the z coordinates are all set to 0. And all that's left are just those curves that were of equal altitude. Any questions? Okay, and so there's that. There are some questions about domain in this section. So let's go on and talk about domain. Oops. Okay, I'm having a little trouble. Let's see if I can get this thing working. There it goes. Okay, so without going into a lot of fuss on domain for functions of several variables, I think that you guys know enough to do problems like this. So if I say graph the domain, for the function z, and I can say z or I can say f of xy, z equals the natural log of x squared plus y squared minus 1. As I say, you guys, I think you know enough about logarithms to say that x squared plus y squared minus 1 has to be, what do you guys think? Greater than 0, greater than or equal to 0? Which one? Yeah, greater than 0. So let's just say this is greater than 0. So x squared plus y squared has to be greater than 1. And so if you can test this, the points x, y can't be inside the unit circle because that will have x squared plus y squared less than 1. Can't be on the unit circle because that will have x squared plus y squared equal to 1. So xy is any point outside of the unit circle. Okay, any questions about that? And if somebody made me graph it, I would probably not do the best job. But so there's my units. That's horrible, actually. Here's my unit circle. I'm going to clean that up a little because it's bad. Like that. And then I would shade on the outside of that. I think I'll try that again. Okay, any questions? So, you know, and I don't know how to annotate. I might just go x squared plus y squared equals 1 and point to that circle there. Okay. So any questions about that? So domain, pretty straightforward. If you use set builder notation, you'd say something like this: the domain is equal to the set of points x comma y such that x squared plus y squared is greater than 1. Okay, and so that's a way of describing the domain algebraically. And honestly, you probably should be able to recognize either one of those to express it that way or to graph it. It's not a big deal. I am looking to see if there's any questions out there. Okay, here's the other one. So here I'm going to do sort of a 4-dimensional problem where the input is 3-dimensional and it outputs a 4th dimension. So f of x, y, z is going to be simple square root of 4 minus x squared minus y squared minus z squared. So with a 3-dimensional input, that means that level curves become level surfaces. And I don't even know what that means, but we just say level surfaces to sort of remind you of level curves. But they aren't level. And so if the f of x, y, z is called w, okay, and you set w equal to 0, then you've got this, well, you could say 0 is the square root of 4 minus x squared minus y squared minus z squared, and then square both sides. And so you would get 0 equals 4 minus x squared minus y squared minus z squared. So finally, you just say x squared plus y squared plus z squared is 4. And that's a sphere of radius 2. It's a surface. So clearly, it's not level because spheres are not level, but we still call it a level surface. Any questions about that? I'm just going to pause and see if anybody puts a question up. I don't see any hands. Any questions? Last chance. Okay. I think I'll just make one comment. Later, we'll be considering level curves for potential energy functions. And I said level curves. I should have said or surfaces. Okay. So if you think about a level curve becomes an equipotential surface. I should actually say, in this case, a level surface is called, and this is a weird term, but I started it a second ago, equipotential surface. And that makes a lot more sense than just saying a level surface. Equipotential just means everywhere on this surface has the same potential energy. And I'll just do it this way. For gravity in 3 dimensions, I think I'll leave this to you guys to see if you can figure this one out. So for gravity, and I don't mean gravity that points down, I mean gravity that points to the center of the Earth, wherever you are on the Earth. For gravity in 3D, an equipotential surface is the shape of what? And I'm waiting for you, someone to type in. Think about gravity. Equipotential would be a surface in a gravitational field that has the same potential energy. Correct. Thanks, multivariable functions. They would be the shape of a sphere. And so when you determine what gravity is, when Newton first sort of formulated the law of universal gravitation, that law implies that equipotential surfaces for gravity have to be spheres, which is why planets are round, I guess, why planets take the shape of spheres effectively, because those are the equipotential surfaces for gravity. Okay, and you know what? I don't really want to say much more about that. I'd like to give you guys a chance to ask any questions. I see Aaron. No, never mind. Again, you can unmute or you can type a question. This is one of the lessons that I said at the beginning of chapter 14 would be kind of light. And that I probably don't need to test too heavily. Okay, so we're going back into 14.2 now. This is on limits and continuity, which is always it's a trying discussion. Okay, so I want to just, you know, and this is going to be for functions of several variables. And they almost make them, the way they define things, they almost make it harder than it needs to be. It's actually really easy to define limits using vectors that just automatically would include, you know, when you do vector functions that evaluate as scalars, so it inputs a vector and outputs a scalar, it's really easy to define limits using vectors. It's much more complicated to do this with coordinates of points x, y, and z. But this is the route that the books always take because they just don't want to put vectors in yet for some reason. But I would like to sort of talk about just one of the basic ideas for limits and sort of the problem that arises when you do multivariable limits. So I want to first begin with a graph. So let's say f of x. So let f of x be this thing. It's going to be the absolute value of x over x. And you remember maybe that if x is greater than 0, what's f of x? Oh, wait. Yeah, it's just 1. It evaluates to 1 because it's just a number divided by itself. If x is less than 0, it's not less than or equal, less than 0, then f of x is what? Now you have a positive over a negative, and somebody's already typed in -1, so that's correct. So the way this, if you graph this thing, it's just a little strange. You're going to have sort of a hole there and maybe a hole here. And then in red, I'll do the rest of the graph. So it's going to look like this on the right and this on the left. Okay, and so on the right, it's up at a height of 1, and on the left, it's down at a height of -1. Okay, now if I ask you to evaluate the limit as, let's say, x goes to 0 of f of x, what would you say? Yeah, it does not exist is correct. So this does not exist since the one-sided limits don't agree. And you may remember in your 180 class that the right side limit has to be equal to the left sided limit for the limit to exist. So I would say lim as x approaches 0 from the left of f of x is not equal to the lim as x approaches 0 from the right. Okay, so that's a good enough argument for why the limit doesn't exist. Now, in 3 dimensions or higher, I'll say in or functions of several variables, that's easy enough. I'd say this issue is more complicated. the limit must be the same as we approach a point from any direction that we approach in. So the limits, or the limit, must always be the same, no matter how we approach a point. Okay. And I would just add this is difficult because there's an infinite number of paths that you can approach a point along. So this is difficult since any point can be approached along an infinite number of paths. Okay. It's easier to prove a limit doesn't exist than to prove that a limit does exist. So I think I'll just make a couple of notes here. Proving that a limit exists can be very difficult. I'll say is often very difficult. Sometimes you can. I'll show you a trick when you can, but it doesn't always work. Every problem is different. So the method that you would use kind of depends on the problem. But the good news is we're not going to actually ask you to show, to prove these limits unless the limit doesn't exist. And then in that case, we'll ask you to prove when a limit doesn't exist. So let me make this note here. It's easy to prove a limit doesn't exist. You just have to find two paths where the limits don't agree. So just approach a point. I like the way I said that better. So just find two paths to a point where the limits don't agree. Okay. I think that's enough chatter. Okay, I'm going to pause for just a second and turn on some lights. It's getting dark in my room. All right, so now we're going to do another limit very quickly. At this point, we've shown, we did an example where, and the problems are easiest when you're approaching the origin. So that's why you see so many of these where x, y, the point goes to 0, 0. And it's easiest when they do go to 0, 0. Of course, you could do this with functions of 3 variables, but that's just going to be even harder. If we were to do this as a vector function, we could have done it this way. F of r, where r is a position vector, equals some function of r here. Those are easier to do when you use a vector input. We don't get to do that here. And when you do it with a vector input, it covers every dimension. So that's kind of nice. But regardless, I want to do another one here. And just to remind you what we had done on the last examples was we were showing how you could approach the origin along any line if you let y be equal to mx. And when you evaluate the limit, it can't depend on m. Otherwise, the limit won't exist. So the m has to, you have to be able to simplify and eliminate m altogether. Otherwise, it's not going to exist. Remember, when you make y equal to mx, that's approaching the origin along every line except the vertical line. But of course, above, we had done the vertical line here by making x0 down on this case, the second example we did. So that's the vertical line that's not covered by doing y equals mx here. Okay, I want to show you another example real quick. Okay, so here we're going to do the limit as, again, xy approaches 0, 0. And we're going to do this for 2x squared y over x to the 4th plus y squared. Like that. Okay, and you can approach the origin along lots of different directions, but let's do these all at once. So let's do along, as we did on the last example, y equals mx. So this limit, you just make the substitution that y is mx. So and now when I do my limit, having x go to 0 will force y to go to 0 as well. And so you would have 2x squared times mx over x to the 4th plus mx quantity squared, like that. And now this is just a function of one variable now, so we can continue then as x goes to 0. Let's see if we can clean that up. So we're going to have 2m x to the 3rd over x to the 4th plus m squared x squared. So as x goes to 0, I get 2mx. X goes to 0, so I think I just get 0 over m squared here, which is 0. Okay, so I've shown that the limit is 0 along every line. Through the origin. Oops. Except the vertical. Okay, so let's do the vertical line. That's the y-axis. Is where x is 0. So once again, we're going to grab this limit and say, okay, well, here we're going to make x 0. And so you end up with just a limit as y goes to 0 Both variables need to go to 0, so x is already 0. And of course, you're going to have 2 times 0 squared times y over 0 to the 4th plus y squared. And of course, that's just going to be 0. So the limit is 0 as we approach the origin from any direction, as long as you're approaching along a line. Oops. Okay. So the question is that proof? Now you just have to be careful because when we said that the limit exists, you have to approach the origin or your point, whatever the point is. You have to get the same limit as you approach your point along any curve, is what I said, not along any line. So the question is, if we've proven it along any line, does that cover every curve as well? And so that's what we need to check. I'm just going to demonstrate that it doesn't. So check this out. So let's approach 0, 0 along the curve. And let's just do y equals x squared. Okay, just a parabola, first thing that comes to mind. So here you would have the limit, same limit as before. But here, y is x squared. Okay, so if you force x to go to 0, then y will automatically go to 0 and be constrained to that curve. Okay, but now I'm going to say that this is 2x squared times x squared over x to the 4th plus x squared squared. I don't know if you see it yet, but this is the limit as x approaches 0 of 2x to the 4th over 2x to the 4th, which is 1. And when we approached the origin on every line, in every case we got 0. But here, if you approach along this curve, y equals x squared, you get 1. So this proves that the limit doesn't exist. So that's just crazy. I want to pause for a second and see if anybody wants to ask a question. And while I'm waiting for that, no, actually, I'll wait. I'll just wait. What you really want is to see a picture of this curve, because when you see it, you sort of go, oh, I get it. So I think the best thing to do here real quick is I'm going to pause my recording. So on this surface, this top ridge here is the curve y equals x squared. So when we said that y equals x squared, I was restricting motion to that curve. So you can stay on top of this ridge as long as you stay on the curve y equals x squared. But if you approach the origin on any other curve, you will fall down. So I'm going to sort of draw another path, maybe going this way. And in the end, I fall down and I end up down at 0. Okay, so that's supposed to be a straight line curve that I just drew in black there. If I follow that straight line curve, I will go, the limit does go to 0. I'm going to do it. Okay, so that's a straight line path. Okay, so is there any question about that? You get 1 if you stay on the ridge, you get 0 if you approach along a straight line, and it doesn't matter what straight line you approach along. Okay. Now somebody was, it was Jia Hui, was asking up here on the vertical line where x is 0 here. Just notice that the numerator is 0. So what you have here is 0 over y squared, which is 0. Does that answer your question? Oh, you're right. No, it's not, because remember, y is, it's because x is 0. Remember, when y approaches 0, you have to remember that y is not equal to 0. Always with limits, you approach, but you never become. So x is 0. This point has to approach the origin, but you cannot allow it to touch the origin. It's okay for one coordinate to go to 0 as long as the other one doesn't. So I'm allowed to say x is 0 as long as y isn't 0, because I haven't touched the origin. All right. And if x is 0, I have 0 over y squared, regardless of the value of y. Does that help? You just have to remember, when y is going to 0, you have to always stipulate that y is not 0. It's very close to 0, but it's never equal to 0. Any other questions? Okay. Okay, I think I'll start up again here. And so, you know, this is just to sort of give you a sense of how this works. I'm going to start my recording up again. Oh, I never stopped it. That's fine. Okay, now I want to do one more example here. Okay, so here I wanted to do functions of x squared plus y squared. So sometimes, oops, if x, y approaches 0, 0, we can substitute x equals r cos theta and y is r sine theta. So basically you put it into polar coordinates. Okay. Note x, y will approach 0, 0 by letting r go to 0. Okay. Any curve can be covered this way by allowing theta to continue to vary. So this can follow any path. To the origin. if we let theta vary freely. Okay. If this results in a limit that is not dependent on theta, then the limit exists. Let's just say it this way. If the limit can be evaluated, and the result exists and does not depend on theta, then you've proven that the limit exists. I'll just say you've proven the limit. And this is the only proof of a limit that you'll have to do. Okay, so let me do a quick example. We're going to do lim as x, y approaches 0, 0. And let's do, just this will be super easy. Let's do the sine of x squared plus y squared over x squared plus y squared. Okay. And then the obvious substitution is, x is r cos theta, and y is r sine theta. Any questions about that? So I'm going to say, all right, well then that's just a limit as r goes to 0. So now it becomes a one variable limit, which is awesome. Because we know lots more about those, and you can use L'Hopital's rule on this, and any other rule you want to use, you can use for one variable limits. And by the way, this is a one-sided limit. You don't have to think about r being negative. Okay, so it goes to 0 from the right side, if that helps. That would be fine. So anyway, you would have the sine of r squared over r squared. Because as you know that x squared plus y squared is r squared. And you switch to polar coordinates. Oops, sorry, I did not mean to do that. Don't know how that happened. And then I might do another substitution just to make this a little more clear. So here, maybe I would let u be r squared. And so you could say that this is the limit of just sine u over u. And then you would argue, well, if r is going to 0, then of course u, which is r squared, is also going to 0. So you could say, just let u go to 0. And somebody may remember, I expect somebody remembers what that limit is. Right. Thanks, Fawn. That's 1. Okay, so the limit exists. And is 1. Okay. And so limits, we've got, you always need limits before you can do derivatives. And derivatives are coming next. In the next lesson, we'll be covering partial derivatives. Then many of the theoretical theorems require something that you've heard of before in the single variable context, and that is continuity. So continuity is also defined in terms of limits. So we'll go ahead and put this down, definition. So we could say f of xy is continuous at the point AB if the limit as x, y approaches a b of f of xy is equal to f of ab. Oops, that should not have an equal sign, I'm sorry, in front of the f of xy. Okay, so this is equal to f of ab. So basically this is just saying you can evaluate a limit by just direct substitution for continuous functions. Okay, also, f of xy is continuous on the region D in the xy plane. So now I'm going from being continuous at a point in the first statement to be continuous in a region. And of course, that would just mean that it has to be continuous at every point in the region. So f of xy is continuous on the region D in the xy plane if it is continuous at every point in D. And I should say, this is easiest if D is open. Open sets that don't contain their boundary. Okay? So this is a set without a boundary. And it's more complicated if D includes boundary points. But we're not going to spend a lot of time on making a big fuss over this. I think you all have a pretty good intuition for what a continuous function is. So there's no issue there. And then before I take questions on this, I would just say trig functions, exponential functions, logarithmic functions, radical functions, polynomial functions, rational functions, are all continuous. Oh, and let's say, and combinations of these, I'm going to say, let's say most combinations of these are continuous on their domain. Okay. Exceptions exist. And I'll show you what I mean. So let's first add to this, absolute values are not included. in lists like this. Because absolute value, you can do all kinds of weird stuff with absolute values, as evidenced by the very first example that I gave, which was the absolute value of x over x, which is not a continuous function on its domain. So, oh, I should, yeah, we'll leave it at that. So exceptions are going to be functions like you know, absolute value of x over x, which has a discontinuity of 0. But also, like the square root of x squared over x. There's no absolute value there. And the problem, as you know, is that the square root of x squared is just the absolute value of x. So this is combination of a radical and rational functions. Okay. Still not continuous at 0, but that's just like any other function that's not defined at 0, so it's not a real big deal. What you really want to focus on was just basically all these guys are continuous on their domains, except for really weird cases like I've given you. And in all of the normal cases, continuous on their domains means that you can just evaluate, you know, it's just a statement up here. You can evaluate limits by just substituting the values in. And that's all we mean. You know, if it's continuous, you can evaluate limits by substitution, and you don't have to do any hard work on that. Okay, so I think that's all I need to say there. And therefore, I'd like to give you guys a chance to ask any questions on this. And then after that, I'm going to open the floor up for homework questions. So I'm just going to pause for a second and wait.